Welcome to Texas State University's Organic Chemistry 2342, Organic Chemistry 2. We're going to continue on with Chapter 14, Part 2, Aromaticity, specifically benzene and why we can call it an aromatic compound. Okay, so there's, in the early days of looking at these organic compounds, they noticed there was an unusual reactivity. The first was that the hydrogenation was not as exothermic as expected for something that is unsaturated, because double bonds have a higher potential energy than saturated hydrocarbons. And so by adding hydrogen across that double bond, you release energy. Okay. But then they also noticed that it wasn't undergoing some of the other reactions, including additions across the double bond, addition of bromine across the double bond, or water across the double bond. And so this led us to something must be different about benzene. Something must be different about this particular compound. And it even react differently than dienes would. So when you start looking at it and you think about having a double bond, you would expect for it to react with bromine to get an additional product to give you a system here. But if we react benzene under those same conditions, we don't get a reaction. If we have this double bond and we wanted to take it with water and an acid catalyst, we would, of course, add that across there, get a hydrogenation product. We don't see that. In benzene, there's no reaction. If we wanted to oxidize this down to an aldehyde or a ketone, depending on the substitution here, we would use potassium permanganate right here, and that would oxidize the material down to some kind of carboxylic acid or an aldehyde or a ketone, depending on the substitution pattern. We don't see this reaction happen. And when we do hydrogenation, it takes place very slowly and takes place at much higher temperatures than it should have if it was just an unsaturated system. Okay, so one way to measure that stability associated with having this benzene being aromatic is actually look at the hydrogenation energy. So if we look at the values of hydrogenation of a double bond, and we think about that as the idea that that double bond is storing energy, and when we go from that double bond to that single bond, we are releasing energy. So to keep all things the same, to make sure we're comparing apples to apples, we're going to take cyclohexene, which has the same number of carbon atoms as benzene. However, we only have one double bond in cyclohexene. And if we hydrogenate that, we can measure that hydrogenation to release 120 kilojoules per mole of the material. Okay, so what that's saying is that one double bond in a cyclohexene configuration will release that much energy. Okay, so if we add a second double bond, in theory, it should be twice as much energy released when we do this. And so it should be about 240 kcals per mole. But what we observe is actually 232 kcals per mole. Now, in this 1,3-cyclohexadiene, they are conjugated. So the difference in the calculated versus observed is the direct measurement of that conjugated stability that we learned about in the previous chapter. Okay, so now for your information, if we went from the 1,3 derivative to the 1,4 derivative, where they're opposite each other and not in conjugation, it is actually measured to be 240 kilojoules per mole. Okay, so if we do the same kind of reaction with benzene, we expect it to be 360 kcals per mole, 120 kcals for each of the double bonds. However, when we hydrogenate benzene down to cyclohexane, we only release 208 kilojoules per mole of energy. That means there's a difference of 152 kilojoules per mole. Okay, that difference in energy is what we call the resonance energy. Okay, so the benzene ring is stabilizing that much more energy in there. It has that resonance energy is basically stabilizing that system such that it actually has less energy to release during this hydrogenation process. Okay, so that means that these things have to be different, okay? And so Kekulé came up with the idea that these compounds were aromatic, okay? Partially because they tend to have unusual smells based on the other uh, other unsaturated compounds, but also they have this high resonance energy. So there are 4 rules we must follow to make a compound aromatic. The first rule is the compound must be cyclic, okay? We're gonna start with just one cycle right now, and we will extend that later, okay? But it must be cyclic. We also must have an uninterrupted uh, string of p orbitals. Every single atom in the ring has to have a p orbital available to donate to that cloud. Okay. Now, to make sure those p orbitals are overlapping properly and sharing properly, the molecule must be planar. Okay, so that all the p orbitals will fully overlap around the ring. Okay, and the last rule is the pi cloud must contain an odd number of pairs. Okay, so one way to think about that mathematically is we can just say, okay, if there are 4n plus 2 electrons in our system here, 4n plus 2 electrons in our system, then that means that we would have the correct number of electron pairs. So let's look at that n number. That n number can be any number from 0 to 100. It doesn't matter. We just want to know how many electrons we should have. Okay, so that means if n is 0, that means we can have 2 electrons in our pi cloud, and it can be aromatic if it satisfies all the rules. It must be cyclic, must be uninterrupted, must be planar, and it must have that odd number of pairs. So 2 electrons is 1 pair of electrons, so that's an odd number. So if we put the number 1 in for n, then we have 4 plus 2, which is 6. That's the number of electrons we have in benzene, and that gives us 3 pairs of electrons, okay? And if we add that, go up to the next number, which is 10, we would have 10 electrons in our p's right there, which gives us 5 pairs of electrons, which is an odd number. Okay, so that's the meaning of the 4n plus 2 rule. N can be any number, and it just helps us account for how many electrons we are looking for in our pi cloud. Okay, so now that we have what aromaticity is, we also have a compound that's called anti-aromatic. Okay, and so anti-aromatic means that they are similar in structure in every way except for the number of electrons. And because of this, they are not as stable as their aromatic analogs or their aromatic similar structures because they break one rule. For anti-aromaticity, you still have to be cyclic. You still have to have a p orbital on every atom in that ring. The molecule must be planar. However, now you can have an even number of pairs of electrons. What that means is that for your Huckel rule changes to 4n, and n can be any number from 1 to 100. It doesn't matter. So what that will give us is if n is equal to 1, that means you have a total of 4 electrons, which is 2 pairs, okay? So that means anti-aromatic compounds are an even number of electron pairs, okay? Aromatic is an odd number of electron pairs. Anti-aromatic is an even number of electron pairs. What if you break any one of these 4 rules? If you break any one of these 4 rules, you cannot be aromatic, anti-aromatic. That makes you non-aromatic. Okay, so let's talk about aromatic, okay? Cyclic, planar, completely conjugated, and having an odd number of pairs of electrons, or a 4n plus 2. So those are numbers 2, 6, 10, etc. For anti-aromatic, you have to follow all those rules, but you have an even number of pairs of electrons. And if you break any one of those 4 rules, you are non-aromatic. Okay, so let's go over a few compounds to double check to make sure we have an understanding of all 4 of these rules for aromaticity. Okay, so let's look at these compounds here at the bottom. Annulenes are monocyclic hydrocarbons that have alternating single and double bonds, and so those can go anywhere from 4 to any even number of bonds. And so as you go to 8, 10, 12, 14, 16, they can all be in a planar or non-planar configuration depending on how the bonds are alternating. Okay. So if we look at this first one right here, we have cyclobutadiene right here. Okay, so it is cyclic. We meet that rule. Every atom has a p orbital. How do we know every atom has a p orbital? Well, we have a pi bond here, and a pi bond is made up of a p orbital on this atom and a p orbital on that atom, because the carbons are sp2 hybridized, meaning that two of the p's are in our hybridization, leaving one p available for that pi bond. So we have a pi bond on each of the carbons in that ring. Therefore, we have a p orbital on every atom in that ring. So we've met the first three rules. But how many electrons do we have in there? We have one pi bond, and that has two pi electrons, and a second pi bond, and that's two more pi electrons. So we have a total of 4 pi electrons, meaning we have 2 pairs of electrons. That is an even number of pairs of electrons, making it anti-aromatic. Okay, let's apply these rules to benzene. We know it's aromatic, but let's make sure, okay? So first of all, we have a sp2 hybridized carbon on all 6 members of that ring. We have a pi bond on all 6 members of that ring. So we have 6 pi orbitals, and we have 2, 4, 6 electrons in that system. That fits the 4n plus 2 rule, and it has 3 pairs of electrons for each of those double bonds, meaning it meets the rules for aromaticity. Cyclic, p orbitals, planar, and an odd number of pairs. Okay. So let's look at those cyclohexatriene right here. In this configuration of cyclohexatriene, because it's sp2 hybridized, each of those bonds is trying to be 120 degrees apart. Unfortunately, in this all cis configuration, it actually is not planar. It actually pooches up in what we call this little boat or bucket kind of configuration, okay? So it is actually not planar, so therefore it doesn't meet the third rule of our system. It is cyclic, it has p orbitals on every single atom, but it's not planar. And in addition, it also has a total of 8 pi electrons, which is an even number. So if it was planar, it would be anti-aromatic, but it's not planar, so it breaks 2 rules of aromaticity. Therefore, it is non-aromatic. Okay, so let's look at that and what kind of things that we can have in there. Does the thing, everything we've looked at right now, have an even number of atoms in the ring? Can we have non-even number of atoms in the ring? And the answer is yes, as long as you meet all of the rules. So let's look at this compound right here, the cyclopentadiene, okay? And it has an sp3 hybridized carbon here. It has 2 hydrogens right here. So we meet number 1, it is cyclic, but every atom in the ring does not have a p orbital. Because this is sp3 hybridized, there is no available p, and therefore we've broken a rule. In addition, that cyclopentadiene part actually pooches up a little bit and breaks planarity. Okay, so in what we looked at before, we saw things that had no charge. Well, what if we had charge? Can that actually apply to our aromaticity? And the answer is yes, if you follow the rules. Okay, so let's actually take one of these protons off right here and make a carbocation on this. Now we have to remember that our carbocations are sp2 hybridized, trigonal planar, and it has an empty p orbital. Okay, so there's 0 electrons in this p orbital here. Okay, so now let's look at our rules. We are cyclic. We have a p orbital now on every single one of those 5 atoms. Okay, and we are planar now because it is all in the sp2 hybridized orbitals. Okay, but we have 0 electrons in this orbital. We have 2 electrons here and 2 electrons here for a total of 4. So that means the cyclopentadiene cation is actually anti-aromatic. It follows all the rules, but it has an even number of pairs of electrons. Okay, so we have that p orbital, we've got that sp2 hybridized carbon. Now, what if instead of having it be empty, what if we put 2 electrons in it? If we did that, we would go from it being a cation to being an anion, because if we have those 2 electrons in that p orbital here. Okay, now let's apply our rules. We have cyclic, we have a p orbital on every, because this is still sp2 hybridized. we are planar. And now we have 1 pair, 2 pairs, 3 pairs of electrons. We have a total of 6 electrons in p orbitals. Therefore, the cyclopentadiene anion is an aromatic compound. Okay, so that's showing you that why you can actually have different sized rings, and as long as you have those p orbitals and the right number of electrons, you can have a wide variety of structures. Okay, so let's look at the transition going from the cyclopentadiene to the cyclopentadiene anion. And to do this, we have to change the hybridization at this sp3 hybridized carbon. If we take away the hydrogen and leave the electrons from that sigma bond and put those in that new p orbital that we generated by removing that hydrogen and changing the hybridization, we will end up with a total of 6 electrons, or 3 electron pairs, in that anion, and that anion is now fully aromatic. Okay, are there other ways to do this? And yes, there are. We can actually extend these rules a little bit from monocyclics into polycyclics, okay? So the 4n plus rule applies to only monocyclic systems. So how do we apply that to multicyclic systems, okay? In multicyclic systems, each of the cycles must follow the rules of aromaticity, and we just need to make sure we're looking for the electrons in the right place. So in the case of naphthalene here, if we look at this side of a naphthalene here, this looks an awful lot like benzene. So we're going to say, yes, okay, that part of the naphthalene, it definitely meets all of the functions. It's 6-membered ring, it has 3 pairs of electrons, it's flat, and it has p orbitals. Let's look at the other one. So if we look at just this side of the ring here, right here, we see that it looks very analogous to that of the benzene, and so both of those rings satisfy the aromaticity rule. Therefore, naphthalene overall is aromatic. Okay, so let's do that same kind of analysis on anthracene here. This first ring right here, oh, it's got 6 electrons in there. That's easy to see. Let's look at the second ring here. Oh, that looks like benzene too. It's got 6 electrons here. Ooh, let's look at that last ring. Can we find 6 valence electrons in this last ring? Well, we have 2 here, we have 2 here, but we also have 1 electron in that part of the pi bond and another electron in that part of the pi bond. That means we have a total of 6 electrons in that last ring. Therefore, it is aromatic. And if we start looking for those electrons that are split between in a double bond, but within a ring, we can see that all of the compounds here actually are aromatic and follow all of the rules, okay? So one of the ones I want to kind of draw our attention to is if we look at this one right here, okay? So this end right here, everybody's like, oh, that looks like benzene, that's obviously aromatic. Let's look at this particular ring right here, okay? Let's try to find all those electrons. So we have 2 electrons here, but then we have 1 here, 1 here, 1 here, and 1 here, for a total of 6 electrons in those p orbitals. Therefore, it satisfies the rule. Okay, so we have aromatic rings. We know we can make these p orbitals available to us on carbon atoms, but is aromaticity restricted to carbon atoms? And the answer to that is no. We can actually add other heteroatoms to the system, and a heteroatom is any atom other than carbon. Okay, so for example, it can be oxygen, nitrogen, or sulfur. Those are very common. And to be part of the system, it still has to have a p orbital and the right number of electrons. So when we have something other than carbon, we have to make sure that the hybridization is correct to allow us to have a p orbital, and that we have electrons that are either in or not in that p orbital, depending on the structure. So let's look at pyridine right here. In pyridine, we have, this is our 2 electrons with carbon, this is a 2 electrons here. And if we actually looked at the hybridization of the nitrogen here, that hybridization on nitrogen is an sp2 hybridized nitrogen. Okay, so If it's sp2 hybridized right there, that means it does follow the planarity structure because of its trigonal planar structure, but it also has an available p orbital because of its hybridization. So if we look at this and look at which electrons are contributing to the aromaticity, we have to compare the electrons that are on the nitrogen here and the electrons that are in the p orbital, okay? The lone pair of electrons on that nitrogen are actually in the sp2 hybridized orbital, meaning they do not contribute to the electron count in aromaticity. Okay? Only the one electron in the p orbital on the nitrogen is in that count. And so we have a total of a one pair, two pairs, and three pairs. So we have 6 valence electrons, or a total of an odd number of pairs. And these other electrons are actually not contributing to the aromaticity, but they are available to act as a Lewis space. And we'll show that in chapter 20. Okay, so let's actually start looking at where the electrons are in this particular atom here. In this case, we also have an sp2 hybridized nitrogen here, but we have, instead of having the lone pair be in the sp2 hybridized, the lone pair actually resides in the p orbital, okay? And the hydrogen bond, the bonded hydrogen here, is in that sp2 hybridized orbital. So now we have 2 electrons in this p orbital, plus 2 electrons, plus 2 electrons. We have a total of 6 electrons available to us in our p orbital. It is planar, it is cyclic, and has a p orbital on every single atom. So it meets all the requirements for aromaticity. Okay, and that aromaticity can be extended out over multiple rings with multiple substitutions by different compounds. So one of the more common ones are these nitrogen and oxygen containing heterocycles here. And the lone pair here is actually not participating in the aromaticity, but in parole, the lone pair is participating in the aromaticity. Now, if we switch out nitrogen for oxygen here, we have a slightly different situation. We have 2 lone pairs. And in this case, one lone pair is contributing to the aromaticity. The other lone pair is not. It's in its hybridized, sp2 hybridized orbital. Now, if we move on to sulfur to demonstrate that as well, we again have 2 lone pairs. One lone pair contributes to the aromaticity. The other lone pair does not. Okay. So we can, just like with other multi-ring systems, we can have mixed all carbon rings and heterocyclic rings. For example, in quinoline here, we can have just one nitrogen. If we can even have mixed 5 and 6 membered rings now that we have these lone pairs available to us to be able to dump into our aromatic ring count. And we can add multiple substitutions for carbon even. As long as we meet all of our requirements, these are aromatic compounds. And we can even extend that to 4 substitutions or more. So now that we know that we can have these rules of aromaticity apply for all carbon systems or carbon and heteroatom systems here, what is their driving goal in all of this thing? The stability of being aromatic drives many of the properties we have here. And the last property I'd like to talk about is this drive to become aromatic, changing the acidity of an sp3 hybridized carbon-hydrogen bond, okay? So if we look at just the hydrogen at the end of something like ethane, that's an sp3 hybridized carbon, and we know that's the least acidic type of carbon-hydrogen bond, and it has a pKa of around 60. Okay, so those are very hard to remove. In fact, we rarely ever actually remove those with a strong base. We use them as a base once we create them. Okay, however, if we have this sp3 hybridized bond in conjugation with a double bond, and we have an opportunity to, if we were to remove this proton, these electrons would be donated into an aromatic system. It actually lowers the pKa, or makes that more acidic. It brings that pKa up all the way to 15, which is about as acidic as water. So it's very easy to remove that proton from the cyclopentadiene to turn it into the cyclopentadiene anion because the energy it saves by being aromatic. Okay. Now, once we do have that aromaticity, one of the reasons that this cyclopentadiene anion is so stable is because we can use our normal resonance structures to show that we can spread that charge out over all 5 of those carbon atoms just by moving our electrons in and then moving our electrons in and up and in. We can move that anion all the way around the ring. And that's why many times we actually see the cyclodipentyl anion written as the negative charge in the middle of the ring in the cycle. Okay, so this is just another demonstration of knowing that aromaticity is actually helping save energy, and it increases the acidity of that sp2 hybridized, that sp3 hybridized hydrogen, giving us an aromatic compound in the cyclopentadienyl anion. That concludes chapter 14, part 2.